So basically, you have the exact labels of each data instance, and you collect them. You put it into a database, and you train a classifier. For example, the most simple classifier could be Sophia vector machine, and things like you tell Sophia vector machine, okay, I give you this input, and output should be which class, benign, malicious, which content, and then eventually the machine learning model will memorize somehow the statistic association between input and output. Say which features indicate the maliciousness of the instance. For example, in the malware, like maybe in ransomware, you will see some file encryption indicator. Say there's a file encryption operating inside, and possibly this is a malicious. So this is kind of like a statistical correlation that the machine learning model trying to memorize. No matter how complex the machine learning model would be. For example, nowadays we're talking about a deep neural network. The same thing. They're trying to memorize the statistical association between input and output. And the information you tell the machine learning model is the supervised data, like fully labeled data. You tell which class each instance belongs to. Okay, so this is a supervised learning scenario. So what if like there are several bottlenecks of supervised learning? For example, most of the case, you don't have fully labeled data points. Most of the cases, I would say, you collect the files, you collect suspicious files, and this file just appear once in our database. So we call this one singleton files. You have no evidence say this is a malicious or benign. Don't know. So you cannot give any labels to such a singleton. So you just put in the database and say, okay, this is unlabeled. All right, so for intrusion detection as well, like most of the cases, you collect data and you cannot differentiate this is benign or malicious. Maybe it's just like some abnormal things, but you're not sure it's malicious. So in database, you cannot put exact labels for such cases. Also, outside the security domain, like a medical image, like robotics, like recommendation systems, it's very hard to give people a clear answer. This is a good or bad. This is true or false. So it's very difficult to do that. And unless you can put a human expert sitting there all day and looking into each instance, otherwise, like you cannot generate a fully labeled data sets. And then this is first bottleneck of supervised learning. Second part is like, well, if your learning task change, for example, your behavior can be drifted as well, like from time to time. Let's say if we're talking about some user behavior of computer inside the company, and if we switch user roles from developer department to financial department, of course they use different tools. So their I/O behavior, like traffic I/O behavior, will totally be different, but they're benign. So if you switch from one role to another role, the behavior will be changed as well. So we call this one like concept drift. Once you have this concept drift, if you change the benign data, and then you have to, what you do is like a retrain your classifier so that you can recognize correctly what will be the benign and the malicious behavior given some scenario. But sometimes the retraining can be really painful. It's like that can be huge. Collecting new data points, collecting new labeled data points can be difficult. So retrain from scratch, sometimes it's not affordable. And remember, like in our case, like the network attacks and malware analysis can be really dynamic. So the things can be changed very quickly. And then you have to update your model continuously with a very frequency base. And this is difficult. And so it's like what keeps your data is a long tail. The long tail data is like that. So normally, like in long tail data, you have most of the data points, maybe 99% 99 data, just concentrated in a very small area. But left 0.1 data points, they will have very large variance compared to the others, and they just appear really, really rarely. Let's say like in medical diagnosis, like we know like a tumor is really rare case to the whole population. I mean, lower than 0.1%. So it's really difficult to collect enough data to analyze the profiles, the tumor. So that's why like we call, if we have long tail data, most likely like your model will focus on the data points in the head area. So the data appear a lot of times. So your model will focus on that area, but your model will fail to recognize the data dropping to long tail area because they appear really rarely in your training database. So how can you handle this case in supervised learning scenario? Like people always talk about like an imbalanced training data set, or we can have some weight training. But it really depends on your understanding about database. If you know this is long tail, and of course you can have some training periods, training checkings here, but in normal cases, you don't have such a beautiful curve to describe the description of database. It's not possible. So how can you adapt your model to such a case? So that's meta learning is proposed. If you supposing like in our cases, you have some experience of learning maybe 100 learning tasks before, like you already recognize which kind of like a content components like observed before. Now you have experience with that. Now how to transfer that experience to the new tagging scenario, to a tag scenario. For example, like in the database, like for example, I think previously when I worked with Norton, they have like a data center. So they retrain the outlier detector on a regular basis, on a monthly basis. Then the things like they're trying to make use the knowledge they have before. They know which are benign, which are malicious. Then make use of the knowledge to identify if new data come in. I can use my past knowledge to decide which are malicious, which are benign. So that's to say, like if you have enough past knowledge, how can you make use of that knowledge to guide your learning, guide your model adaptation in the new cases? That's a simple example. Like supposing like we have some small bot, like small agent, just trying to do the gradient descent in one. We're trying to optimize the machine learning model. So you just like sliding the ball along the loss landscape of the learning model. So the ball will follow the gradient descent direction until it reach the minimum value of the optimization value, optimization function. And then you have previously you have several cases that know like how you can sliding down fast until you reach the convergence. Now you reach new cases where you've never seen that before. Maybe the shape of the landscape is very complex. So in that scenario, like if you don't have any knowledge about how to slide in your bow, you might choose a random direction and you may stuck somewhere. So that's why like if you use gradient descent blindly over any kind of like a complex optimization problem, you might get issues like you're stuck into local optimum and never jumped out, right? But how about like if you learn some similar landscape before, you see some landscape quite similar with the complex landscape I see now. If they are very similar, you might borrow your knowledge about sliding your balls before and reply that technology here to try to guide your gradient descent direction in the new landscape. So that way you can converge fast in the new problem. So that's an example like how you can transfer the knowledge you learned before to the new task. So another example that we usually have in the meta learning side, supposing like we have several learning tasks before that is not directly related to the learning task we see now. See here, like currently we have a learning task trying to differentiate dogs and otters. Okay, this is what binary classification problem. But before I never have otters, I never have dog image. I only have two tasks. So I have learned something from a cat, differentiate cats and birds. I can differentiate flowers and bikes. So how can I transfer the knowledge here to the task of trying to differentiate dogs and otters? So this seems like undoable at the beginning, but actually the point is like if you can capture some part, like if I want to differentiate bikes and flowers, maybe I'm just trying to capture this one is the key point of the bikes. And you want to kind of differentiate cats and birds, maybe like, okay, the wings can be the key points to differentiate them. So your model is trying to capture, okay, which are the parts that can separate two classes of images as much as possible. So I use that part of the key features and trying to do classification. So this capability of capturing the key features, differentiating two class images, this is a knowledge that I learned before. So I don't want to learn something from background, right? I don't want to learn something from color because it's not totally relevant with the classification goal. So I can try to transfer the capability of capturing the key shapes or key textures in the image. And the technology capability here is trying to capture, okay, if the two images, they contain different textures or different shapes of the objects, I use that to differentiate new classes. So that's why we can transfer knowledge here. And that's what machine learning trying to do. So from the previous task, they're trying to give a model a prior knowledge, which part of the feature about the learning task you should focus on, and which part of the feature you should probably remove from your knowledge space. And with that selection of features, and you can apply that feature selection result over the new task and help you to better adapt to the new task, even though you don't see any kinds of example before. Okay, so the key point is if you want to transfer the knowledge from the past to the new task, so you have to learn some prior knowledge about your classifier. Of course, the learning task shouldn't be changed so much. You shouldn't be changed from, let's say, image classification to voice classification. This is not doable because the feature space is totally different. The feature space can be totally different, so you cannot. There's no hope you can transfer. I'm saying if you're working in the same domain, like for example, you're trying to classify malwares that were collected in 2018. Okay, now you have new malwares coming from 2020, 2021, 2022. So you have the time interval in between. I'm sure about there will be some big change about that malware families. But what about how you can classify? Your customer might capture the signatures, or how to capture the signatures inside the analysis result of malwares, and you apply this capability over the new task. And if possible, you can identify the signature inside in the new task. So this is the capability of how to capture the signatures or indicators that will be called a prior knowledge about your classifier. And this is the key to success of method learning. And the method learning is trying to learn how to learn those prior knowledge that are encoded in the past jobs. So, and this is, let's back to the supervised learning. It's a little athletic stuff. So, okay. So let's start from that. Then let's say this is your training data, B is the training data, and pi is your model parameters. Okay. So usually for supervised learning, what you do is if I have my training data composed by X and Y, and X is a feature and Y is a label, I have my training data. So then I want to maximize the likelihood of my model parameters so that my model can best describe my training data, which means in this case, if this is supervised learning, that means your model will capture as accurately as possible the statistical association between X and Y, right? This is supervised learning. And if you add some Bayesian theorem here, and you can decompose the learning objective into two parts. One part is okay, what if I have the prior probability over the model parameters? So model parameters can be, you have a support vector machine, you have a W1 X1, W2 X2, plus B equal to your classifier. And on each WI, you might have some initial guess. What will be the possible value for this W? Then you have a range of this W. For example, you range from -1 to +1, right? So this is the range. You don't need to guess from minus indefinite to positive definite. You don't need to search the whole range. You only need to shrink your search range with a very small area. So this is called the prior probability of your model parameters. So that one will constrain the shape of your model. If you have very accurate information about your model, so yeah, you know exactly the value of your model, so your regularizer, your prior knowledge will be very strong. So which means they constrain the search range of your model. You should choose this model. You shouldn't choose the other model. Okay. So this is the role played by the prior knowledge. And the second one is data likelihood. Data likelihood is I really have my training data in the new task, and I want a model to fit my new task as much as possible. And this is a term depends totally on the data. If you change your data, your likelihood will be changed, and you should change your model. Right. So this part is really depends on the quality of training data and the volume per size of the training data. And here's like you see here's the trade-off. Say, okay, first, if you either way is like you have really huge number of training data, and this way like you don't really count on the prior knowledge because we have enough data. So I'm sure we can get capture the accurate statistical association between X and Y. I don't really care about the constraint. All right. So second extreme point is like you don't have many training data points. You might have very little training data points. Your training data point has limited coverage, for example, like that. So you can say, okay, if I use my current training data set, it's very probable that my model get overfitted to this small training data set and cannot be generalized to a new case, right? So in that case, what you do is like, okay, can we constrain instead the models? So my model shouldn't be searched in a very large range. So I just like give a very strict constriction of my model parameter values. So what you do is like within this constraint area, I try to find some model parameters that best describe the training data. So in that way, like you can try to avoid the overfitting. One example is like if you train DNA model, I'm sure like some of you already have the experience, like painful experience of training deep neural networks. Say if you have really limited training samples, all right, and then you train deep neural network without any kinds of like regularization, you just push your model as complex as possible. Then what you do is like your model will 100% perfectly fit your training data. Like I can recognize each training data point very accurately, no mistake, right? So 100% TPR. But the problems like with that model, you apply this model to a new scenario, to a new example, you maybe have the issues like I will fail to recognize the new stuff. And this is called overfitting because your model is like, can only present the training data. There's no way they can generate new things. And in this case, if you look into your model parameters, you will see your deep neural network is very complex and you have many layers, you have many neurons, and each neuron will have parameters, non-zero parameters. So this is the typical case. So typical regularization is like, okay, I want my model parameters as fast as possible, which means like I want most of my deep neural network parameters to be zero, right? So even though like you can have like 100 layers, each layer have 1,000 neurons, then the neuron will have links between each other, but most of the link will be shrink to zero. That means like your network structure is intrinsically very simple. You don't have many links inside. And in that way, your constraint over sparsity of model parameters plays a role of prior knowledge. And they think your training data should be very simple. You shouldn't use very complex model to feature data. And they put that kind of knowledge as a regularization term here. And they constrain the model choice. And eventually you choose the right model for your data, and it can be generalized to the new data cases. So that's what we have in the typical supervised learning scenario. Basically, we can summarize them in one sentence, like the more training data you have, the better the training data becomes in classification tasks. So that's the general recipe. But in other cases, like if we have enough training data, we don't care about the second case. And if we have limited number of training data, we do need a second term to help us to get over the issues of overfitting. All right. So then the knowledge, the prior knowledge, like the knowledge, the constraint you put over the model parameters, and this knowledge is that what you learned from the previous task, and is what you want to extract from that meta-learning scenario. For example, like you have like really a lot of data, like we collect in the past, you can accumulate it year by year, and eventually, I'm sure each team will have a huge database that we can collect in the past. And this past data, even they're old, they're different from the new cases. They can be used to learn a constraint over the model parameters. For example, the simple case, what will be the range of model parameters? and possibly to be chosen in the in the new task, which will be the model parameters that you shouldn't choose in your learning task, because when you choose that in the past, they will fail your classification task. Or which kind of model architecture you should choose or you should prefer in your learning task, which model architecture you should skip, because they always fail your previous learning task. Okay, so that gives you the prior knowledge about your model, and then you can say, okay, once I have this very strong constraint, I might be able to train your model properly with very few training samples collected from new tasks with that constraint over the model. So that's basically the pipeline of meta learning. But if we put in this way, it's like a supervised learning, all right? So the case is like you have to count on training data to maximize the likelihood of your model parameters and get your model. And if you have limited training data, what you can count on is like we should have very strong additional constraint over the model. And this additional prior knowledge is given by the previous learning experience, which is given by previous learning tasks. And in this case, like we have named the previous learning task as the meta training database. So meta training database means like they can come from different learning tasks. Now we are talking about like we're trying to do malware classification over specific malware families, right? So this is about our current learning task. Previous learning tasks can be totally different from that. I can say like previously I don't want to do malware family classification, just want to do detection. But I also accumulate a lot of malware database, a benign database that collected from past years, and the past data can be totally different from the current database. But there might be something we can share, but the knowledge we can share is reflected by the choice of the model parameters and the choice of model architectures. And that's the noise we want to encode from the past learning task. So we say like in the past learning task, all of the training data and testing data belonging to past learning task will be presented as a meta training database and a meta testing database. We call it meta because this is more broad. In a more broad sense, the previous learning task cover more broad knowledge compared to the current learning task. It's more, let's say, it's less specific, let's say. Less specific because we can cover a lot of different learning tasks before. And the current task is very specific. I just want to focus on this case, not the other case. All right, so yeah. So the case will become like that. You have your meta database that coming from past experience, and now you might have a few training samples that collected from current specific database, right? So which notice deep. And based on your past experience and your current limited training data, you combine them together, you only get a proper model. So this is object function of the meta learning task. So here's like, okay, now you see here, if you want to do image classification, I want to say, okay, this is darkest, so this is this is I don't know what's the this is a walk, this is some other stuff. All right, so before you don't have such a task, you don't need to handle this task. Before you have the task like, okay, I want to say this is a finger, this is a tank, this is a mountain view, whatever. So all of those previous database, they will accumulate this meta database and make use of the previous database and trying to get some knowledge about my model and then apply this knowledge about my model over the new task and make use of limited number of training data set and apply so far with the specific learning task and to get my model derived properly to deliver accurate and generalizable classification output. Right, so this is a general pipeline of meta learning. So let's put it again into mathematical stuff, how we conduct such a meta learning stuff. So let's say we introduce the metadata training data set, metadata training data set. Okay, so that may include several learning tasks. So for each learning task, it's composed by the training samples and the labels. Right, and the D is the limited training samples that we collect so far with respect to a very specific learning task we want to process now. Okay, so this is the learning objective. We count on the meta experience and the current experience trying to learn a proper model. So then like we don't really want to like something very simple strategies like you have all the past database. And now you have very small piece of database that focus on current work. How about like we combine all of the database together? We get a really huge database and we try to classify whatever, so get something output, right? So this is doable. This is doable. And actually, I know someone just has done such an experiment and it works. But the problem is like with the increasing size of the meta database, you cannot always do the retraining. Right? So but maybe in our case, it's possible. Like the model samples are really difficult to collect year by year. Maybe eventually, it's just like maybe 100 gigabytes. It's still doable for GPU machine. But think about like medical image and natural traffic and, for example, like also image recognition. You cannot accumulate all the training database together. It's not possible. So you don't want to keep this one. What you want to keep is like if I have my previous database, my previous learning stuff, and we estimate what will be the possible range of my model parameters. Can you give me some estimate about my model's profile? Which means like, okay, in the, let's say you're talking about a linear model, and you have 1,000 parameters in your linear model, W1 to W1000, okay? So you can imagine like in the model space, this is a 1,000 dimensional space, and each dimension corresponds to one model parameter. And what you do is like, okay, if you don't have any constraint, I want to search my models in a 1,000 dimensional model space. This is really hard. And what you want to do is like, give my past learning experience, I want to constrain my search range within this 1,000 dimensional model space to a very small subspace. That means like I want to put some guess about upper bound and lower bound of model parameters, right? So if I have this knowledge, I can use this knowledge inside the estimate of my proper model given the current task. So things like, for example, here, you can guess, okay, give the meta training base, what will be the distribution of my model parameters. And actually, they can, for example, like they can give you a Gaussian distribution for each model parameters, like your mean values here, your variance is there. And given that probability distribution over your model, and you put that estimate into your estimate of your model and combine with your current model, current training data, and with the very small Gaussian distributed model parameters, you choose the best model parameters to fit your model instead of searching the whole range of the model parameter values. So here, I give you the weighted, let's say the weighted maximum likelihood solution, but the weight depends on the distribution probability of your model parameters and determined by the distribution of the meta training database. So what you can do is like you decompose the learning object into two parts because you take the integral that's difficult to do in a gradient way. So decompose into two parts. One part is like first, let's say if we have the meta training database, so what will be my possible model parameters will be. So I want to estimate my model parameters at distribution given the meta training data set. And once I get this theta star, which is the distribution of my model parameters or the average of my model parameters according to past experience, once I have this initial estimate of my models and put that initial estimate into the learning problem of my current learning task, and start with this theta star as the initial data points, initial model estimators, and start from that. I do, for example, like a gradient descent using the training database B here, and I can reach the convergence point of my learning problem as fast as possible. So this task is not very obvious for classical machine learning model like a submodel vector machine, because you know submodel vector machine is a convex problem. You can always reach the unique maximum point. of your likelihood function, right? So that's the subtotal machine. It's very beautiful. And that's why people don't really worry about that. You give me limited number of training samples, okay, I can use like a regularizer or the subtotal machine. I can still reach the maximum. And it's unique. I can guarantee that. But for deep learning neural network, it's different things. Like maybe you try your deep neural network before. Like you start from different initial data points, then your model will converge at different points. And if you slightly change the random initialization of your deep network, you may end up with the models like providing different accuracy score. And that could be very sensitive. That's why like in machine learning papers, people play with the random seeds technique. Let's say they declare the model reached some 99% 99 accuracy, but actually they play with the random seeds. If you play that random seeds for several rounds and take an average, it's possible their accuracy is not so high. Okay, so that's why like in deep learning, there's a famous issue like random insensitivity to random initialization. But here, like say, we don't initialize your model over your current task randomly. We initialize your model with some guess, with initial guess that we learn from the past data. That's why like actually you fix the starting point of your optimization or gradient descent search. And you start from a very promising starting point that are very close to the real global minimum of your optimization problem. If you start with that, you can converge really fast. Don't need many data. That's how machine learning can really speed up the convergence of the training process. All right, so that's the general mathematical principle behind. But let's see how does it go. So let's say first step, we want to say, okay, I have the meta training database, and once I might have meta training database, I want to generate some model. And this model is, you can imagine this model like encoder. Okay, I just take the past database, like a D-beta training database in, and output will be the guess of your model parameters, like imagine model parameters. Supposing you have, again, let's take an example like a 1,000 model parameters, like linear model here. So the input will be all the training data that collected from your past learning tasks. You have maybe 100 learning tasks before, then you have 100 different training databases before. And all of those 100 training databases will be input to this function. And output of this function is 1,000 different model parameters you estimate that might be suitable for the current task, right? So you see here, this is a multi-input, multi-output system. It's like, let's say, decoder stuff, right? So we want to decoding the data that you collected from your past learning tasks into a model, the estimated model parameters. Like you want to do this transformation. So that's what you do with this one. So how can I train this model? How can I train this decoder model? So like, let's say like before you divide each your learning task into training and testing part, which means like supposing you have 100 learning database before, 100 different learning tasks before, and each learning task will have a training database and testing database. And the training database we call it meta training database because they cover a lot of learning tasks. And testing database we call it like a meta test database because of the different learning tasks. And what you do is like I want my decoder structure to output a model parameters that can reach as low as possible classification error over the meta testing database. That means like I want this decoder model to give me a good estimate of model parameters so that if I use these model parameters over the testing database of all the past learning tasks, I can guarantee a good classification accuracy. So this is like from statistical view, it's like if I can guarantee my model perform really good, really well over the past learning task, I have enough confidence to say in new learning task, my model will perform good. Because the logic is like, if I only have one single learning task before, it's not guaranteed because probably you are overfitted to the previously unique learning task. But supposing like before you have 100 different learning tasks that cover different domains, that cover different learning problem, your class label could be totally different. Then that means like you have a really little chance to get stuck over some local optimum or got overfitted to one specific problem because you have so many different problems before. And that way, like we can guarantee your model have enough diversity to capture the nature of different problems, capture the classification boundary of different problems. And if we make sure our model can perform really well on previous 100 different learning tasks, and this is a empirical guarantee, say like our model can really capture the intrinsic features or important features that can be applied to different tasks, then that gives us the reason to believe with that feature, with that selected features, with that selected model architecture, we can perform well over the new task, since the new task might share the similar feature space with before. So it's possible like we can capture the key features in the new space. Okay, so that's what we do. It's like, okay, so the key point of meta learning is like trying to learn such a decoder that we can decoding the training data we collected before to a model parameters estimate. And this model estimate will be supposed to be performed really well over the testing database that we collected before. Okay, so this is the general idea of the meta learning, how we learn such a decoder. All right, so that's the Euro structure we have. Like say, this is the training database. We put into the green frame, all the training database belonging to the learning task we collected before. And the blue frame just telling us what will be the testing data set belonging to the different learning tasks we collected before. And now we put into the meta training database. Supposing like we have the decoder like this structure, right? The decoder is like that. So yes, like you put each training samples or each batch of training samples that we collected before into this. Supposing like this is the recurrent neural network, so that you put the first batch, second batch, third batch, you can get your model evolve until reach convergence here. So that will be your estimate model parameters step. And your estimated model parameters will be applied to the testing database that you collected before, and you get your prediction output from your over the testing database that you collected before. And you can measure what will be the loss over the testing data point. So eventually, your estimated model will supposed to be providing really good accuracy over the testing database that we collected before. We call the meta test. So your model parameter 5 star here is supposed to get really accurate classification over the meta test data set XTS. Right? So this is a meta training. And here we put it in a more explicit way. Like, okay, so F theta here, that's the model decoder. You can use recurrent neural network. You can use CNN, whatever. So the input will be the training database that we collected before is MetaTrain, and output is the model parameters, exact model parameters. You have 1,000 model parameters, you have 1,000 output here. Okay, and this is constraint, right? This is a constraint, and this means like by putting DI training, so MetaTrain database, you get the finite, which is the model parameters, and you apply these model parameters to your meta testing database over each learning task we collected before, and this decoder is trying to get a model estimate that achieve the best accuracy over the previous meta test database of each learning task. Okay, so this is the whole optimization problem of meta training. Yes, it's complex. So usually people trying to optimize this problem in the alternative way. So it's like we can first freeze theta. We freeze the decoder, and we try to get finite and put the finite into this optimization problem, and I try to optimize my theta. Okay, but then I can say, okay, with the new theta here, I generate a new phi and put phi here. So it's like each time, like you have to freeze your theta somehow and try to get what will be the gradient of your theta, and you're trying to update your theta afterwards. So that's the general way of meta training. But there's a different way of concrete way of conducting such a training process. For example, here, like how you can get this model parameters. It's like we can simulate the gradient descent of model optimization. So you put a recurrent neural network here, put neural network via STM or the sequential data. So each module of the sequential data will take each batch of the meta training database. Like for example, you can split your meta training database into chunks, and you just put one batch into one module of this sequential data, and the input could be totally random initialized the model parameters, and then this is the input. There's a random data point. Random model parameters, and this is the first batch. And after the first batch, you do gradient descent, then you have a updated model parameters here. And this is the second batch, you update the model here. And the third batch, you update the model here until you reach the final model parameters. So this is a recurrent neural network trying to simulate how your model are updated in the optimization problem. Okay, and then once you get that, and you can apply this model parameters to the testing database. Since you already know your model architecture, you just like place this model parameters into your model and get your output from the meta test database. Okay, so what's the bottleneck? Okay, so this is the flowchart of that. So first you need to sample your learning tasks. You either basically traverse different learning tasks one by one, or say just randomly pick one learning task like I collected before. Suppose you have a huge learning task data set before. What you do is you want to randomly search one of them and try to do stochastic gradient. So which means you can save some time and efforts. And then for each learning task, you divide the database and from this learning task into training and testing. And then what you do. And what you do is I give this training database into a decoder, and the decoder gives me the model parameters, and to put model parameters here, I get my loss function, I get my gradient with respect to the decoder's parameters. So what is the bottleneck here? The bottleneck here is the decoder is really complex, because supposing different network, usually you talk about the millions of parameters. I think in ResNet 18 or ResNet 50, they have 2 million parameters inside if you use fully connected network. So 2 million. So which means if you use this technology to meta train your ResNet 15 or ResNet 50 models, you're going to have I don't know what is the input dimension, but I know without dimension is 2 million. So given this complex model, I'm not sure you can really converge to get a stable estimate of your decoder. And if your decoder gives you really a very broad range of model estimate, that's not useful, because you really want you have a reduced range of your model parameter choice. So that's why in this case, this method has such a bottleneck, a complexity bottleneck, that you cannot train a decoder that can recover 100% of each model parameters. Right? You cannot do that. So how can you alleviate that problem? It's we're trying to go back to the meta training process. So in meta training process, you have a pre-trained model, and this pre-trained model coming from all of the learning tasks you collected before. Okay. Let's say you have 100 learning tasks, and from 100 learning tasks, you can train a pre-trained model. You can download this pre-trained model and combine with some of the training data points you have, trying to fine-tune with several rounds of gradient descent, you get your personalized model. So that's the basic idea of meta training. So how we can simulate this process, right? So supposing theta here is the pre-trained model. One of the example of pre-trained model is I don't know whether you guys have idea about GPT-3, GPT-2 or GPT-3. And this is a pre-trained model because it's pre-trained by Google. No one can repeat that training again because that's really expensive. So what you do is like you want to use GPT-2 in your application, you just download this model. Maybe you have your own training data, so you update the GPT-2 parameters by several rounds of gradient descent, normally no more than 10 rounds of gradient descent. Then you get your personalized model to fit your own natural language processing tasks. Okay, so that's an example of the pre-trained model. And CETA here, let's say CETA here is a row of GPT-2. It's already trained with someone else. I don't want to change them. Okay, I download it, and this is my current training database. My training data I have. Maybe only have limit number of training data with 100 data points. I don't care. And what I'm do is like, okay, I just calculate the gradient value of the model parameters, pre-trained model parameters, using my current training database, and I just do one-step update of my model, because this is the key idea for fine-tuning. You don't need to train several, hundreds of rounds until convergence. You only do 1 or 2 rounds of gradient descent to update your model. That's enough for personalization. So 5 here is the customized model parameters. Eventually can feature testing, feature learning tasks. Okay, so your fine-tuning process can be approximated by the one-step gradient update based on the pre-trained model and based on the trained database you have, right? So what you want to do, you want this pre-trained model, you want this fine-tuned model to perform really well over the testing database you have. So what you have is I put 5 here. I put 5 here, and I want to apply 5 to the testing database, and has my loss function here, and I want to minimize this classification loss function over CETA. So which means I wanted some pre-trained model. If this pre-trained model can only get one-step update using my own training data, and after that, my personalized model can perform really well over the testing sample. I just want to find how to estimate such a pre-trained model that can easily adapt to my task by 1 round of gradient descent operation. So CETA here, you see here, CETA here, the pre-trained model here is the variable of this meta-training problem. So I want to find a good initialization point of my model. Okay, so this is the idea, we put the meta learning into optimization problem. So how to do that? Oh, battery is running low. Oh. Right, so what you do is okay, let's sample several learning tasks. I have my learning tasks learning task 1, learning task 2, learning task 3. Right, so I will start from my pre-trained model. So my pre-trained model could be something here, something here, something here. I'm not sure. So okay, normal training space is okay, I start from this one. I have enough data of my learning task, so I start from this point, go down along gradient descent direction until I reach my my convergence point, phi 2 here, because this is the best point. That's the model I want to estimate. Or say I start from here, I go to 1 or 3 if you have enough training data. But now the things you cannot move to that point because your training data is not enough. So what you want is can I have a good initialized model guess that can fastly adapt to my my learning tasks. Supposing this is the best model I can estimate. And then what you want is I want my initialized models which is pretty close to all of the 3. So the point is okay, if you want to have a fast adaptation to your learning task 1 to 3, what you want is shall we just start at the closer point to learning task 1 to 3? So this is the best model that I can estimate for each task. So what you want is you want to choose a middle point somehow, pretty close to 1, 2, and 3 together. Okay, so I can reach this task. How I can reach this one? What you do is okay, I start from random model parameters, and I calculate the one-step update using my training data collected before for learning task 1, learning task 2, and learning task 3. I just do one-step model estimate. So I do 1 here, and 1 here. Okay, you possibly after one step estimate your model parameters here, and here. Okay, so you make an average of the model parameters. You make an average, simply model average, and you end up here. So here is what you need, because this is the model estimate that pretty close to the best model for each learning task. But here it's like, I don't think this here is usable, because you cannot use a meta model for classification. That's the key point. You cannot expect a meta model is usable. And since like this one is never close to any of the convergence points, and I would say here it's like a pre-merger model. It's like early stopping. You just early stop somewhere, right? But I would say like once you start from this data point, what you can do is like, okay, I just do one step within descent, I can reach my best model of each learning task. So that's the key idea of this approach. And in this approach, I would say like the simple point is like you don't need to really train a decoder. And the decoder simply train data, output these model parameters. It can reuse the decoder to any of the learning tasks. You don't need to have this parametrical model. What you do is like simply average your one-step update of model parameters with respect to each learning task. So in this way, there's no decoder training. So you only make the average of them. And since there's no computation cost for decoder training, and there's no difficulty of parameter estimate for decoder and respect to high dimensional problem, right? So this is the basic idea. And this good thing is like this model doesn't really count on which model architecture you're using. You can use Singer, you can use software vector machine. I don't care. What I do care is like what's your gradient direction. And after following that gradient direction to do one-step update, just do the average model parameters. And this way, I don't really care which model I'm using. I just trying to max some of them and take an average. And that's all. Okay, and this is the best paper back to 2000, SML 2017, and published by a stellar researcher in the UCLA. And I think the lady is still very famous in this domain on meta learning. And right now, she steps into meta reinforcement learning domain as an even more challenging strategy. So that's something we can use meta learning. I know it's like quite far from your domain, but let's say we trying to keep open mind because we can try to find similar perspectives. And say here we're trying to do image classification. And there's a application of image classification called the few shot learning. So what is the few shot learning? It's like I recognize cat, dog, birds, flowers, cars, ships. Okay, but now there are some tasks asking me to recognize which is rocket and which is tank, which is lion. I don't have such training data before. But in the new learning task, I only have maybe 1, 2, 3, very small number of training data points, training image, let's say. This is called a few shot. Or in the extreme case, this is one shot learning. It's like I have only one example image of the new class that people want me to classify. I only have one image of tank, one image of rocket, one image like whatever object that appeared in the new task, right? So what you do is like, okay, you have all the training images that I collected before that is not directly relevant with the new class that I want to classify, right? It's not directly relevant. There's no overlapping between each other, right? So I have a lot of basic classes. What you want to learn is like I want to learn a representation. I don't want to learn the classifier. I don't want to say, okay, because in the new classification problem, there might be a lot of classes, and the number of classes can be different. Let's take an example. Recently, I think Elena has been doing some intrusion bottleneck traffic classification, and she's working on CTU13. It's an old database back to 10 years ago. And in the database, we have 13 different bottleneck complaints. But now we have a new database. And this database is possible in the new database, we have more or less bottleneck complaints. But one thing I can assure is like there won't be exactly 13 bottleneck complaints. So which means like if you want to do complaint classification, your classifier will be considered to be to output a different number of classes in the new task. But how to present the bottleneck traffic, and that is something we can remain, and we inherit from previous task, right? So same thing here. You want to learn some representation model, like feature encoding model, that we can track features from the previous image. And from meta learning, what you do is like I have a meta feature tracker. All right, you have a meta feature tracker, and using this meta feature tracker, and by updating this meta feature tracker using the given number of training images that you have in your new task, you can adapt your feature tracker to the new task. And this feature tracker can help you to capture features, to differentiate different classes of training images in new tasks as much as possible. It's not guaranteed. I know it's not guaranteed, but I can. But by this meta learning task, I want to find some feature representation can best separate the possible classes existing in the new task, because this meta feature tracker performs well over the previous learning task. So this is the first thing, and based on the features features you learn here, and you can attach some classifier. Supposing you know like how many different classes you have in the new data set, like 5, I can apply a softmax with 5-dimensional output here, combined with a features trained from the images, and do classification. All right. So in this way, you trying to inherit knowledge about feature extraction, feature presentation about your previous data set. And same thing can happen here. Supposing we're talking about bottleneck traffics, we can really generate some feature presentation of bottleneck traffics that we learned from before tasks. And then we use exactly the same feature extractors to the new bottleneck traffics. And hopefully that the feature extractors can work well. The new task can generate accurate feature presentations, differentiate different bottleneck compounds, and we can attach a classifier here. Supposing we know how many different bottleneck compounds we have in future, then the attached classifier here, we can do the compound classification. So that's the idea. And same thing can be applied to malware.
But what's the difference with the fine-tuning that we saw previously? We're using the same model to learn a new task.
Yeah.
I didn't
Which one?
Understood the difference between the fine-tuning and the few shot learning. The fine-tuning of GPT-3, for example, and the few shot learning. Yeah. I didn't understand the difference.
The fine-tuning, well, I would say like the same. They are the same thing. The few shot learning is like okay, one simple solution is like you can train from scratch. I have only one image. I don't care. I just put one image into my learning process. I have more. But definitely doesn't work out, right? So what you do is like you can fine-tune a pre-trained model, but what is the best pre-trained model you might have? And that's important because GPT-2 is something they give to you. You don't have any manipulation over the pre-trained model. You cannot control. They give they give you something and you accept that stuff. So meta learning is like supposing you can control the training data that the people to train this pre-trained model before. You have the control over the training data. And you want to train a best pre-trained model. And this best pre-trained model can really fast adapt to your learning task. Okay, so that's the difference. In fine-tuning, you cannot control the pre-trained model. So you have to say, okay.
So now I have access to the weight of the pre-trained.
Exactly.
Okay.
You have access to the previous training database. That's the difference. All right, so second use is like trying to adapt model architecture. And it's also related to AutoML technique. It's like how you choose the most proper model architectures to my task. So classical ways, like let's do some neural architecture search. So how many layers I should have, how many neurons for each layer I should have. So you do some cross-validation until you reach some the best settings of hyperparameters. Okay, so this is the normal way, and this is really time-consuming because once you want to do this search, you have to train your model, testing your model, training your model, testing your model for several rounds until you reach the best guess about the hyperparameters. But for usually meta learning, we can try something easier, like we can free some part of the models, and we want to train the rest part. The rest part usually like a task-specific, like classifier module of the DNN. So what you do is like from previous task, I want to learn what is the meta model for my classification module in the deep neural network. I freeze the feature presentation part, okay? It's a different case as before. So I learned a meta model about my classifier. Then what I do is like, okay, in the new task, I have several training database. I update the model parameters about this meta classifier. So the meta classifier can fast converge to the classifier, the best fit to my case, okay? So I don't really need to explicitly say, okay, how many neurons I should have, how many layers I should have. For example, like how do you set like a dropout ratio about my classifier? I don't need to do all of the settings. All I need is like I need a meta model. I need a few training data points. I can combine those and fast adapt to my task. I don't really care about it, the other hyperparameter settings. So it's easier than conducting like the neural architecture search, the MLaaS method from scratch. All right. So of course you can use meta learning to guide your gradient descent, because they can learn a meta gradient descent way. So that tell you, okay, normally you should follow that rough way to go to the gradient descent, but you have really a large variance. For example, you follow a tube. What you follow is a tube to from the starting point go to the convergence point of optimization problem. In this tube, you can choose any track in this tube. Okay, you can choose any track in this tube until you reach the convergence fast. But how do you constrain? How you describe the shape of the tube? How you constrain the boundary of the tube? That the meta model can give to you. Meta model can give to you what is the model parameters of your gradient descent, what is the variance of your gradient descent. So once you know what is the typical mean value of gradient descent and the variance of your gradient descent, actually they give the tube of your optimization path, so they can guide you best to fit your task. Final examples like that. So this is the example from the UC Berkeley robot control team. So what they do is like, okay, they have the robot machines here. So the machine operates like they're trying to say trying to pick a bowl and put the plate and put a cup. So that's the two tasks, right? But normally what you do is like you should program this robot. Like say, I put my arms to reach X, Y, Z, and then move my arm from this coordinates to another coordinates, and I do with which speed. So you have to program exactly the coordinates and exactly the speed. And then they can do the programmed action. So that's what we do for the classical control and PID control, like you see in the paper. And then what they do here is like they do a reinforcement learning. Okay, so this is based on reinforcement learning driven control theory. You have a policy model ahead, like you observe where the ball is and what will be the next step. So there's a policy model behind that. But before that, you have to let this robot try many times until you can convert to the policy model. And now they do is like they let this robot trying to observe what humans doing here. And humans like pick out the ball, move to here, put it into that cup, and put it here, put it into the plate. So they put some videos about how human behave to finish this action. And they let the robots to look into this demo video. And several clips of video, after reviewing several clips of video, the policy model of the robots automatically learn how can copy the human's behavior to put the ball into a specific place. So by looking into the video here, supposing like the policy here is totally random initialized, so there's no usable policy at the beginning. So by looking into the different video clips of human experts and the different clips of human experts' behavior, this is the learning scenario or learning experience that collected from the past, already done in the past. And the policy model is trying to learn a meta policy model that we can best fit the previous learning task that recorded in the video clips. And based on this meta policy model that we have, which is basically describe the human expert behavior, And this robot is tried once and try to clarify this policy model, which means like they're trying to update this policy model by its actual action. And then it can adapt to the learning task, which means like they can put the ball in the right place at the right moment. Okay. So this is how meta-learning can use to control the robots. Robots are by looking into the video of human expert actions, right? So then for the moment, there's no direct action application of meta-learning into security case, which is I'm looking right into right now. I look really forward like in a year, we're going to have some results published of this, how we can use meta-learning to detect new attack campaigns, to detect new malware families, to adapt to the new malware classification, family classification task. So this is an ongoing parallel study. Yeah, hopefully I can report the results soon. So the takeaway from the summary, the tutorials, like first, the meta-learning task, the task of meta-learning is trying to generate a good initialization of your classifier or your regression model. That this model can be fast adapt to a specific learning task by using a few rounds of gradient descent and using very limited number of training samples in your task. Okay, that means like meta-learning can reduce the requirement of collecting training data set with respect to specific training database. Okay, so this is the first point from the meta-learning. The second role of meta-learning is trying to say, okay, meta-learning itself is a fine-tuning technique. It's a fine-tuning technique. So difference between the classical fine-tuning and the meta-learning based fine-tuning is like meta-learning can control the training data set and testing data set in the previous learning task. And that means like you can choose which pre-trained model you start with. And that makes a difference, right? So you're given a free pre-trained model, you may end up with a really bad convergence or really bad model adaptation to your task. So you not control that. But from meta-learning, it's like you can use the training data and testing data you learned before to choose a best pre-trained model so that it can fast adapt to your own learning task. That makes a difference. It's a data, let's say, it's a data-dependent fine-tuning technique compared to data-independent fine-tuning technique that you have with GPT-2, you have with BERT language model, right? So last line is like use meta-learning. It's promising like we might have some solution to handle long tail training instance. Long tail training instance, like for example, like at the beginning, you might don't have such a long tail training instance in your database because this training instance just appears so rarely in your training data set, so you don't have them in your previous learning task. But now comes a new bunch of training data, and they do have such a rare training case. So how you can adapt your model to classify this rarely appearing training instance? So we can use meta-learning because meta-learning don't really ask us to provide so many label data points to update your model. You can really use a small piece of a training data set, which is rarely appear in the whole scenario, to make your model converge to the new learning task fast. So, okay, so the third point that from meta-learning. Okay, thanks a lot. If you have any question, please feel free to ask.